Welcome to This Explainer. Today, we're diving straight into the gritty reality of systems integration. We're going to open up the case files on 6 real, downright sneaky robotics bugs that were caught by a CI/CD platform. We're looking at that incredible breakdown of what actually happens when pristine software meets the messy real world, and how software in the loop, or SIL testing, is often literally the only thing standing between a clean code commit and a very, very expensive hardware disaster. Let's get into it. But before we put on our detective hats, we need to establish our core philosophy. It boils down to this. A test suite that never catches a real bug is just theater. It's totally fake. Basically, every bug is a missing check in your system. The 6 specific stories we're about to unpack, they represent full-blown integration disasters that absolutely would have exploded on real hardware if they hadn't been caught in the loop. Now, to solve these mysteries, we aren't just randomly tossing print statements into the code and hoping for the best. We rely on a rigorous 5-step debugging loop. Step 1, what exactly failed? 2, which layer caught it? 3, can I reproduce it live? 4, what's the working hypothesis? And 5, definitely the most critical, did I actually validate the fix for the root cause? This process ensures we fix the underlying issue, right? Not just slap a Band-Aid over a symptom. So here's our roadmap for this explainer. We'll start with the silent QoS mismatch, move on to physics meets algorithm, then tackle linter and tooling traps, investigate the environment drift, and finally wrap up with the merge Q constraint. All right, section 1, the silent QoS mismatch. This brings us to bug number 1. Let's track down this first bug. Picture this. It was a completely silent failure that froze the entire system for a painful 45 seconds. So during a routine smoke test, the clock and odometry data arrived perfectly on time, no problem, but the IMU and scan data, they just vanished into the ether. No errors, 0 exceptions, not a single warning from the data layer, just absolute silence until the test deadline finally expired. Well, the diagnosis revealed a massive fundamental clash in ROS2's Data Distribution Service, or DDS. The sensor bridge was acting as a best effort writer, which honestly makes perfect sense for volatile high-speed sensor data. But the test subscriber? It was using the default quality of service profile, acting as a reliable reader. And here's the catch. In this protocol, pairing a reliable reader against a best effort writer is an incompatible combo. The result is just brutal. It drops all messages without a single log warning. The fix was literally a 1-line update to explicitly pass the sensor data QoS profile to the subscriber. Simple, right? But this brilliantly illustrates ROS2's most insidious bug class. Because sensor streams are best effort and commands are reliable, a QoS mismatch will just silently fail on you. The huge takeaway here is that you absolutely must explicitly match your quality of service profiles. And please, always assert those configurations in your smoke tests so they don't hide from you.
Moving on to section 2, physics meets algorithm. Bug number 2.
This next case is honestly the absolute star of the show, and it proves exactly why physical simulation is mandatory. The symptom was bizarre. The robot was commanded to reach a target of 3.0 meters, but it abruptly slammed on its brakes at exactly 2.68 meters, falsely claiming there was an obstacle right in front of it. The path was completely clear. So where on earth did this phantom obstacle come from? By logging the robot's physical pitch right alongside its LiDAR data, the root cause finally emerged. Forward acceleration actually caused a physical effect. The robot's body pitch nosed down by about 3 degrees. This physical tilt pointed the LiDAR straight downward. The beams hit the floor, reading less than 0.40 meters, and the algorithm did exactly what it was programmed to do. It detected an obstacle and stopped the robot. The software was flawless, but the physical dynamics created a massive false positive. To fix this, the physical chassis needed some serious stabilizing. They added a second front caster to give the robot a solid 4-point stance, dropping that pitch down to near 0. They also tuned the wheel servo, bumping up the proportional gain, or KV, from 0.5 to 5.0 to get faster convergence. The critical lesson here? Standard unit tests are never going to catch the chaotic interaction between hardware physics and software algorithms. You absolutely need that SIL layer to catch these emergent physical behaviors. Section 3, linter and tooling traps. Let's look at bugs 3 and 4. Let's speed things up a bit and group together 2 really devious mysteries where our own local developer tooling completely betrayed us. So in bug 3, the C++ linter suddenly failed the build. Why? It demanded that the standard math library be included before the GTest header.
It turns out the CPP lint tool counterintuitively classified the Google test header as a C system file based entirely on a regex rule. The fix is super annoying but simple enough. You just separate gtest into its own include block at the top to satisfy the linter's strict opinionated conventions.
Next up is bug 4, which is the classic developer nightmare. A pre-commit check gave a totally happy false pass on a local machine, but then immediately failed the second it hit the CI pipeline. The diagnosis? Well, the local pre-commit tool only processed git-tracked files. Because the developer hadn't staged the newly created files yet, the tool just ignored them locally. But CI, of course, tracked everything, and it immediately caught the formatting drift. These back-to-back tooling traps highlight a fundamental truth of software engineering. Local green simply does not equal CI green. You have to enforce strict workflow hygiene. It's absolutely crucial that your local commit process, like just remembering to stage your files before running pre-commit, perfectly matches the exact logic that the CI pipeline is going to use. Otherwise, you're just tricking yourself.
Okay, section 4, the environment drift. This is bug 5.
This next case investigates an incredibly sneaky missing dependency that hid in plain sight for an entire development phase, and the symptom struck at literally the worst possible time, release day. The Docker release workflow for version 0.1.0 failed because a package couldn't resolve a brand new package called autonav_nav. This was totally baffling because this exact setup had passed every single local validation check up to this point. The culprit? A single missing line in the Dockerfile. Locally, validation was using a shortcut. It just copied the entire repository into the build path, bringing that new package right along for the ride. But the actual release Dockerfile relied on explicit copy commands written in an earlier phase. Because the specific copy command for the new package was never actually added, it was completely missing from the final build. It stayed hidden because that strict Dockerfile only ever ran during the final high-stakes release process. The fix was just adding that one copy line, but the big takeaway is way more important. Your validation environment must be completely identical to your ship environment. If you're shipping via Docker, your CI has to run a true Docker build. Relying on parallel shortcut paths that happen to work locally will eventually, and without a doubt, betray you.
Finally, section 5, the merge queue constraint. Bug number 6.
Let's open up our final case file. This one deals with an infuriatingly silent platform error. The symptom was basically a brick wall. When trying to add a repository merge queue rule to automate integrations, the API kicked back a 422 error code. That's it, a completely empty 422 error. No message, no unauthorized warning, no feature not available text. Just an invisible, silent wall completely preventing the pipeline from advancing. When error messages give you absolutely nothing to go on, you just have to systematically eliminate hypotheses. They tested repo visibility first, making it public didn't fix it. Finally, they uncovered the root cause, an undocumented account type constraint. It turns out GitHub native merge queues require an organization repository, not a personal one. The fix was surprisingly simple once they knew, just transferring their repository to an organization account, at which point that exact same API call was instantly accepted. This brilliantly illustrates our final lesson today. When platform errors are totally meaningless, don't just fixate and blindly retry the same call hoping it magically works. Systematically test your hypotheses. Document your fallbacks so you can keep your momentum going. You really have to understand the boundary of the platform you're using and figure out how to navigate around it. So, we've seen a silent quality of service mismatch, a robot tripped up by its own physical pitch, devious linter traps, Docker drift, and opaque API constraints. Every single one of these bugs was a story of a missing check. As we close these case files, take a hard look at your own pipeline and ask yourself this absolutely crucial question. Is your CI actually mimicking your hardware and ship environment? Are you actively catching these complex, chaotic interaction bugs in the loop? Or are you just performing testing theater? Because if you aren't testing in the loop, you might just be waiting for a disaster in the real world. Thanks for joining this explainer.